So we constructed this supersymmetric Lagrangian in d equals 6, which was just the Yang-Mills Lagrangian plus a minimal Lagrangian for a Fermi field. But there were a couple of gaps in what I told you yesterday, and a lot of questions were asked about them at T, actually, and I wanted to fill in those gaps. So the first question which we might ask is, what is lambda? What I told you was that in dimensions 3, 4, 6, and 10, lambda was a Fermi field in the adjoint representation with the minimum possible number of components. But I'd like to be a little more specific about that now. So, first of all, in 6 dimensions we would have 6 gamma matrices. I usually write capital gammas except in 4 dimensions. So there are 6 gamma matrices, and you can combine them into 3 fermion creation and 3 annihilation operators. So gamma 4 plus I5, gamma 2 plus I gamma 3, and gamma 0 plus gamma 1 you could use as your creation operators, and the other 3 linear combination as your annihilation operators. So if you're just trying to represent the Clifford algebra, you would have 8 states to represent the Clifford algebra. However, I told you that we wanted to make our fermion as small as possible. And in 6 dimensions, we can ask that the chirality operator, the product of all 6 gammas, on lambda should be plus lambda. Now, the reason which it makes sense to do that is that the square of this operator is plus 1. Well, sorry. We can always work. Okay. If you do the analogous thing in 4 dimensions, it won't work out well. You'll find out that the square of this operator is minus 1. So its eigenvalues are I and minus I, and they will then be exchanged by CPT. So in 4 dimensions, if you have one kind of spinor, the Hermitian adjoint field is the other kind of spinor. But in 6 dimensions, I'd recommend you all check this, that you have to use the fact that we're in Lorentz signature. Remember, physics happens in Lorentz signature. You'll get the wrong answer if you try to do it in Euclidean signature. In 6 dimensions, the square is plus 1, so lambda can obey a chirality condition. That would appear to half the number of states. So we'd get 1/2 times 8, which would be 4. And you might therefore think that lambda has 4 components. That would involve the same kind of mistake that we ran into when we used CPT to double the states of a hypermultiplet, to understand what a hypermultiplet was in 4 dimensions. It's true that SO15 has a 4-dimensional representation. We could call it the spinor plus representation. But it isn't real, it's pseudo-real. You're all late, I'm sorry to tell you. And there's a lot of stuff to explain today, so we couldn't wait. It's a very nice exercise to show that this representation is pseudo-real, but I'm going to have to resist the temptation to do it in front of you. If I were doing it, though, I would reduce it to exactly the fact we used yesterday in 4 dimensions about SO4. Now, you can ask me later, but there probably will be other things we won't get to either. Since it's pseudo-real, you need to double it and take an 8-dimensional real representation. Relaxing this condition wouldn't help. That would double the states, but in the wrong way. Then we would have a pseudo-real representation of dimension 4 and another pseudo-real representation of dimension 4. And by the time it was real, it would have dimension 16. So the smallest thing which we can get is to impose this condition, which ends up being 8 real components by the time we make lambda real. Now, the supersymmetry generator was the same kind of animal that lambda was. So epsilon, which is the SUSY generator, also has 8 components, which is 2 times 4. So that answers the question I was asked at T yesterday, why this has n equals 2 supersymmetry in 4 dimensions. It has that because it has 8 supercharges. Neither lambda nor the supersymmetry generator obeys a chirality condition in 4 dimensions. They can't because it would contradict CPT. What they obey in 4 dimensions is this. And the same for epsilon, the supersymmetry generator. So they have both chiralities. All that you learn is that the 4-dimensional chirality is correlated with an internal something. Now we're going to work out the global symmetries of the model. But I'm going to write out the index lambda alpha in a little bit more detail. I'll call it lambda A x, maybe, where A runs from 1 to 4 and is an SO15 index. And x is there because we doubled. We had to double it to make it real. But now that we've doubled it, there's a group, SU2, that could act on lambda commuting with SO15. So we think of S of x as an SU2 index. So we could write this in more detail. I've written it out in glorious detail as something which is SO15 invariant and also SU2 invariant. So we've discovered an SU2 global symmetry that only acts on fermions. You might remember that we had the same thing in the other way of constructing the model yesterday. I hope you remember it. We started with a U1R symmetry that only acted on fermions, and then it promoted itself to SU2 that only acted on fermions. So here, in a different construction of the same model, we have an SU2 symmetry that only acts on fermions. And we also have a U1 symmetry that acts on bosons as well as fermions. So we have U1R that rotates the components A4 and A5, the extra components of the gauge field that become scalars in 4 dimensions. So assuming that the fields are independent of x4 and x5 still lets us rotate that plane. That gives us a U1 symmetry that acts on the scalars. And the lambda has charge, well, plus or minus half of the charge of the bosons. That's the way fermions are. Fermions have half-integral spin. So if we called the charge of A4 and A5 plus or minus 1, we'd say the fermions had U1 charges plus or minus a half. Yesterday, I normalized the fermions have U1 charges plus or minus 1, and I said that the scalar bosons had charges plus or minus 2. I'll stick with that normalization today, I think. And then there's SU2R that, just like yesterday, acts only on lambda. Namely, it acts on the extra index that lambda had because we had to make it real. Now, to show that the model actually is supersymmetric, there's an identity we needed. The identity, as we wrote it yesterday, we were supposed to symmetrize this in alpha, beta, and gamma, and it was then supposed to be 0. The lambdas are fermions, but they were antisymmetric in the gauge indices. So we're going to suppress the gauge indices for this little computation, and we'll just think of the lambdas as bosons. And I actually want to explain to you why that identity is true in 6 dimensions. So we look at lambda in more detail as having an index of type A and an index of type X. So let's say A1, X1, A2, X2, and A3, X3. And there is also epsilon, that is an A4, X4. And what these gamma matrices are doing is combining it into something that's both SO15 symmetric and also SU2 symmetric. So actually it's 0 just because of those properties. We have the 4-dimensional representation of SO15. We've got 4 guys that all transform in that representation. That representation the only invariant in that representation is made with the epsilon symbol. So the only SO15 invariant for this kind of spinor is completely antisymmetric in the SO15 indices, which remember is a spinor index that takes 4 values. I won't quite take the time to prove that. The way I would have proved it, I think, is by using the fact that after you complexify, SO15 is equivalent to SL4. The way it's most often met is that SO6, or actually its spin double cover, is the same as SU4. So lambda was trying to make a completely symmetrical invariant, but the only invariant that there is completely antisymmetric in the SO15 indices. So for Bose statistics, we would now have to antisymmetrize it in the SU2 indices. But since they only take 2 values, we can't antisymmetrize in 3 doublets of SU2. So you see, there's no way to antisymmetrize in the SU2 indices. So therefore, this thing is 0, which completes the proof that the model was supersymmetric. I'll just stop here for a moment if there are any questions on this. No takers? So we need to find the other term in the supersymmetry algebra, the other term in the central charge. I remind you that yesterday at the end of the lecture, one of the questions gave me the chance to calculate for you that P4 became the electric charge. So we essentially did a calculation that shows how the electric charge appears as a central charge. And we also had learned it indirectly because we observed that when we break SU2 to U1, we observed that the W bosons were in small representations of supersymmetry, and that was only possible because their electric charge is in the central charge. But there's another kind of special small representations that we need to understand in order to understand this model. So I want to tell you about that. Now we're going to discuss things that we can see for weak coupling. A general word of advice is that you can't understand what a model does for strong coupling until you thoroughly understand it for weak coupling. It would be like trying to do general relativity without first learning linear algebra, which acts in the tangent space. So in general, what can we understand about the spectrum of a model for weak coupling? What is the spectrum for weak coupling? There are 2 types of particles. There are 2 types of particles for weak coupling. We get 1 by quantizing small oscillations. And it's easy to say what we get. Each field gives 1 particle. But the other thing which we can do is we can quantize classical lumps, classical solitons. So we take our nonlinear field equations and find a solution. Usually, we look for a solution that's independent of time. Usually, this is most frequent, at least in relativistic theories, this is usually most interesting. If this classical solution is stable for some reason, then we find its classical ground state, which will be independent of time so as to avoid kinetic energy. And we quantize. Well, what does that mean exactly? I'll first describe it bosonically. So, our classical solution is some kind of lump. By hypothesis, it's stable. And for simplicity, we're going to assume that the classical solution was unique except for whatever we can deduce from symmetries. Still, there will be a family of classical solutions, phi a of x, which will be phi of x plus a. So quantizing will mean that we have to construct a quantum wave function that depends on a. You can think of A as the center of mass position of the lump that you're discussing. And if you want to know what is an interesting quantum wave function, well, here's one. That describes a lump in a momentum eigenstate. And if you want to know what its energy is going to be, well, first of all, how would you find its energy? You'd find its energy by starting with the Hamiltonian, which would be something like this. And so this is going to be a constant, which we'll call m, the mass of the lump. As I said, to minimize the energy classically, we would have taken phi dot to be 0. But quantum mechanically, phi dot squared is going to turn into minus h bar squared d by d phi squared. And d by d phi acts on all the field variables that the solution can depend on. But the important ones for studying the system near its ground state are those classical variables that don't contribute much to the energy. And the really important ones are the zero modes, A. So this here is going to become something times d squared by dA squared. So our Hamiltonian will be a constant m plus the second derivative with respect to a, and acting one side, it will then give m plus a constant times p squared times psi. And hopefully the constant will come out to be 1 over 2m. What we're getting is the beginnings of a relativistic expansion. The answer really would be the square root of m plus p squared, square root of m squared plus p squared. When you carry out this quantization, though, in the classical limit, we will have a very heavy object that would move slowly. Since p is small, the formula would come out to be non-relativistically. I'm cutting a lot of corners because there isn't a lot of time. if we started with an action, which was 1 over e squared times something, and that's what we're interested in starting with, because what we're doing is finding out what happens for weak coupling. And weak coupling means that E is small. And you see, 1 over e squared appears as a constant in the potential energy. So the mass is of order 1 over e squared. It's because the mass is of order 1 over e squared that near the classical limit, the object is heavy and will be slowly moving if it's not much excited above its ground state. In other words, if we gave it a velocity of 0.1, the speed of light, it would have a kinetic energy that would be 0.01 of its mass, but its mass near the classical limit is very large. So for weakly coupled physics in general, apart from what you get by quantizing classical fields, you get solitons, which I've just explained as briefly as I could. You'll want to learn more about it, perhaps from Sidney Coleman's lectures at Erice on lumps from 30 years ago, if you are interested in working on non-perturbative field theory. Now, the moral of the story is that we found there wasn't a unique classical solution. There was a symmetry of spatial translations that we had to take into account. And we're going to repeat it with supersymmetry. For definiteness, let's take our theory, our n equals 2 theory, which has 8 supercharges. And it's got a supersymmetry transformation, which is delta psi is something. Well, in the 6-dimensional notation, I wrote it yesterday. But you have to remember that mu and nu refer both to spatial indices and to internal indices that correspond to the scalar fields. So, okay. In more detail, there's curvature, but there's also the 4-5 term. That's 2 scalar fields. It's messy to write this out. There's going to be a gamma mu 4 times d mu a4, and a similar term with 4 replaced by 5. So there are various terms that involve either Yang-Mills curvature or else scalar fields, or derivatives of scalar fields. So if we found a totally random, let's first discuss what happens if we find a totally random time-independent classical solution of this theory. Well, in the case of a totally random solution, delta psi won't be 0 for any non-zero epsilon. And therefore, we're going to get 8 fermion zero modes. So if we had a random solution, we'd find 8 fermion zero modes. Let's call them psi 1 up to psi 8. And then we would write psi as the sum of Ci times psi I plus contributions from non-zero modes. And then we would write our Lagrangian for the fermions. Unfortunately, I've called it psi, whereas okay. I've usually been referring to the fermions as lambdas. Let's even change it back to lambda. We had our Lagrangian lambda bar ID slash lambda. Now, what we did for the bosons was instead of treating A as a constant, we gave A a small time dependence. And then we constructed wave functions that depend on A. So we quantized. The equivalent thing for fermions is that, well, C is a zero mode of time-independent equations. But to treat the quantum theory, we have to imagine that C depends on time like anything else. And so the part of the Lagrangian that depends on C there is no contribution from the spatial derivatives precisely because we took a classical solution that was time independent, acted on it with supersymmetry, and got another classical solution. So these zero modes are solutions of the spatial part of the Dirac equation. We let them become time independent, and then the time derivative will contribute. And this is the theory that we've got to quantize in order to find the ground states of the magnetic monopole. The ground states of the quantum states corresponding to our random classical solution. When we quantize it, we'll learn that C is canonically conjugate to itself. That happened because I took a real basis, right? If I hadn't tried to compress this by writing in terms of 8 real fermions, I could have had the guise of positive and negative chirality, and they would have become canonically conjugate to each other. I tried to compress the explanation by just saying that there were 8 real objects. And then when we quantize, we get 2 to the 4 equals 16 states. This is a generic supermultiplet. And it should be. Remember, the generic supermultiplet is the one where no linear combination of the q's acts as 0. And we assumed that for any epsilon, any linear combination of the epsilons, delta psi was non-zero. So we made a kind of classical approximation to assuming that the q's act generically, and therefore we got a supermultiplet of the generic size. Now, that would be fine, but we wouldn't learn anything that's useful for the rest of the lecture. Now, I'm going to instead explain what does give something interesting. Let's suppose we'll pick coordinates in the internal space. So A5 goes to 0 at infinity, and A4 doesn't. So if the gauge group is SU2, for example, we can always do that. Remember, there was a complex number that determined the expectation values of the fields at infinity, and by a rotation of the internal space, we can make that number real, which corresponds to what I'm saying. And now we're going to look for a special solution of the equations of motion, a solution that has some supersymmetric properties. These equations are known as the Bogomolny equations. So first of all, for SU2 gauge theory, these equations have solutions. And those solutions carry magnetic charge. When I say the solution is a magnetic monopole, what I should better say is that the simplest solution is a magnetic monopole. Other solutions have higher magnetic charge and correspond to multiple magnetic monopoles. If you consider a solution of the class, I'm not going to prove this for you, but it's not hard to show that this equation implies the Euler-Lagrange equations of the theory are satisfied. If you look for a solution of the Euler-Lagrange equations that isn't a random solution, but actually does that, then you discover that for half of the epsilons, delta psi is actually 0. You get a cancellation that looks like this. Here's a typical term that's going to cancel. First of all, the equation tells us that F12 is D3 of A4. So there's more stuff, but let's just look at this term. The term, in this expression, there will be 6 terms that aren't trivially 0. I've written 2 of them, and the others differ by permutation of the spatial indices 1, 2, and 3. In this equation, I'm hoping you've all seen the Bogomolny equations and magnetic monopoles before, but I know it might not be completely true. In this equation, I, j, and k are spatial indices that parameterize directions in 3 space. We're looking for a time-independent solution, so it only depends on 3 coordinates. And there's this magic equation of Bogomolny, which not only implies the Euler-Lagrange equations, but it will lead to something more interesting than we had in the generic case. So there are 2 times 2 more terms, but let's just discuss these 2. Since D3A4 is equal to F12, we can write this as gamma 12 plus gamma 34 on epsilon times F12. So it's 0 if gamma 12 plus gamma 34 epsilon is 0. That equation might look a little bit funny, but if you move this term to the right and multiply by gamma 34, you'll discover that it's equivalent to gamma 1234 epsilon equals epsilon. So first of all, from your knowledge of the Dirac algebra, that equation has a lot of solutions because the matrix on the left-hand side squares to 1 and is traceless. It's got 4 eigenvalues 1 and 4 eigenvalues minus 1. And we just keep the 1s. Gamma 1, 2, 3, 4 is conjugate to a matrix that would have 4 1s and 4 minus 1s. So half of the spinors obey that equation. The other half would obey the opposite equation, which we'll come to in a moment. So one nice thing is that this equation had a lot of solutions, but the second nice thing is that the equation became SO3 symmetric under rotations of 1, 2, and 3. In fact, it's even SO4 symmetric, but we won't use that at the moment. Since it's SO3 symmetric, if we'd permuted the indices 1, 2, and 3, we would have gotten the same equation again. So there are 2 more sets of 2 terms I didn't write. They differ by permutations of 1, 2, and 3, and they lead to the same equation. So half the epsilons obey delta lambda equals 0. That means there are 4, not 8, 0 modes Ci, and the action becomes And when we quantize it, we get the same story, but we only have a 4-dimensional Clifford algebra. And quantizing a 4-dimensional Clifford algebra gives 2 to the 4 over 2, or 4 states. So what we've gotten is one of those small representations of supersymmetry that we had before. Now, I'm cutting a couple corners. Something I should tell you is that the simplest classical solution is invariant under spatial rotations. So classically, if we ignore the fermions, it would have 0 angular momentum. Suppose it were a dumbbell, not invariant under spatial rotations. Then instead of the classical wave function without the fermions, depending only in position, it would be like the Born-Oppenheimer approximation to, for example, a diatomic molecule, where you'd quantize the orientation of the object in space. Then you'd get a band of rotational states. That doesn't happen because the simplest solution is rotationally symmetric in space. Now, the rotation generators are just bilinears in the C's, but since we're discussing massive particles, what I'll plot will now be not the helicity, but one component of the angular momentum, Jz. The 4 states will be the same kind of spectrum that we discussed yesterday, except it's massive. What we've found is a massive hypermultiplet. Now, you ought to object that yesterday we learned that the hypermultiplet had twice as many states as I've described. Well, how did we learn that? We learned that by using CPT. So let's apply CPT. CPT will turn magnetic monopoles into antimonopoles. Or if you like, CPT will reverse the sign of the epsilon symbol in the equation. So the equation will look like this. And we'll get a minus sign here. It'll lead to a minus sign here. And therefore, we'll get something which is invariant under the opposite 4 supersymmetries. And we'll have a different set of 4 zero modes. So indeed, the CPT conjugate will double the spectrum. We'll get the same collection 1, 2, 1, but now with magnetic charge -1 instead of +1. Any questions on this? So we've learned that a magnetic monopole, first of all, it has a mass, and secondly, it can have momentum, just like any other particle. And we kind of sketched how to derive at least the non-relativistic approximation to the energy momentum formula. And then we found that it has this internal structure of a hypermultiplet. But there's another very important property of the magnetic monopole, which is that the monopole can carry electric charge. The reason that happens, it's a little bit similar to what I told you about the diatomic molecule. So had the classical solution not been invariant under spatial rotations, we would have gotten a rotational band of states analogous to those of a molecule. However, the minimal magnetic monopole is invariant under spatial rotations. But there is a bosonic symmetry that it's not invariant under. It's not invariant, the classical solution is not invariant under, I'm going to assume that G equals SU2 for simplicity. And we're working in a vacuum where SU2 is broken to U1. The reason we are is that we're trying to understand weak coupling before we try to understand strong coupling. And the theory is really only weakly coupled when SU2 is broken. If we worked in the vacuum where SU2 was unbroken, we'd have the complexities of strong coupling, which are the opposite side of the coin of asymptotic freedom. The classical solution is not invariant under the unbroken U1. So U1 rotations produce a new collective coordinate that maybe I'll call psi. And psi lives in U1 or S1 because psi looks a little bit too much like a fermion. So I'm going to call it phi, which looks, phi is a bosonic field. What's a good name? Okay. I hope I haven't used beta, although no promises. So beta is an angular variable that is an extra classical coordinate for this solution. So when you solve for that solution, it's obvious that it has 3 bosonic zero modes from spatial translations. It's not too hard to see that it's got one more collective coordinate from the possibility of making a gauge transformation in the unbroken U1 symmetry. And because that is the case, the classical solution depends on x, but it also depends on a center of mass position and an angle beta. So when we construct a wave function for the system, it's a wave function that depends on A and beta. I'm ignoring the fermions. The quantization of the fermions gives the result I've described already. And here's a nice simple wave function. Nobody objected to the plane wave for the center of mass, so you probably won't object if I put the internal coordinate in a state that's an eigenstate of the rotation of the circle. But the rotation of the circle is the eigenvalue of the rotation of the circle is the electric charge. Almost. There's a catch which we'll come to in a second. So since n is an integer, but otherwise unconstrained, we get monopoles with arbitrary integer electric charge. So from what I've said so far, the electric and magnetic charge is 1, or plus or minus 1 for the fundamental monopole. And, sorry. Now, this story about the electric charge of a magnetic monopole is one I'm very fond of. So I wrote a very long homework exercise in which I tried to write down everything I thought was really important that I wouldn't have time for. But we're way behind, so there's a lot more stuff I won't have time for. But still, some of the things I won't tell you, you'll have to learn in order to do that exercise. I think you should do it in groups, and I really strongly recommend doing it. It has nothing to do with supersymmetry. But there isn't anything in there that you shouldn't know if you want to work on non-perturbative quantum field theory. I'm leaving tomorrow, but you can ask me questions by email if you're working on the homework. Yes?
So does the entire set of zero modes form a hypermultiple?
Well, yes, sort of. So the zero modes are 4 bosons. That's actually a good question. 4 bosons R3 times S1 and 4 fermions. Now, you see, if we went more deeply into it, we would show that the space of classical solutions is a hyperkähler manifold. So its dimension has to be a multiple of 4. So you're essentially right. This is effective. This space, when you solve for the collective coordinates, you're basically reducing to a problem that depends only on time. In the spatial directions, you solve the equations. So these 4 are a hypermultiplet reduced to 0 plus 1 dimensions. To properly explain that would take a little bit more than I'll say. But that's a way to understand that the 4th direction has to be there. And you could ask, if you were to ask in greater detail than I really have time for, what's the effective theory on R3 times S1? Well, it's essentially the Dirac equation of R3 times S1. And the 4 fermions correspond to the 4 gamma matrices of R3 times S1, that being 4-dimensional. It's a nice story, but we don't have time for it, I'm afraid. Any other questions? Okay. Well, there's a very important subtlety here, which we get if we consider more carefully the quantum mechanics on a circle. When I wrote these wave functions e to the in beta, we assumed implicitly that psi of beta plus 2 pi was supposed to equal psi of beta. I haven't carefully worked out the quantum of electric charge here, but when electric charge 1 here means charge equal to that of a W boson. If you actually look at the homework, as I explained there, I worked there in units where a quark would have had electric charge 1. But I'll explain this today. We won't have any quarks today. We only have W bosons, so we'll think of their electric charge as being 1. So with that understood, I assumed this in the lecture. I assumed this so far. But it makes sense to do quantum mechanics on a circle with the more general kind of wave function. If we do that, then a typical wave function would be the exponential of I times n plus theta over 2 pi times beta. And that actually happens to us where theta is the gauge theory theta angle. I'm going to give a very compressed explanation of why. So what is the gauge theory action? Well, the gauge theory action the usual part is the electric field squared minus the magnetic field squared. But then we've got theta times F mu nu, F tilde mu nu. That's the electric field dotted with the magnetic field. Now, let's just evaluate this action as a function of beta. So we do the same thing we did for the fermions. We let beta be time dependent, and we ask what we get. First, I should tell you, if beta is time independent, we get 0. That's because beta can be shifted by an electric charge rotation. So the action is independent of beta as long as beta is time independent. If beta is time dependent, well, E has a time derivative in it. B squared doesn't, so it doesn't know if beta is time dependent or not. But E squared has a time derivative, and that is going to give beta dot squared. Here we've got something linear in E multiplying B. But B, the magnetic field, has an expectation value in the field of a magnetic monopole. So that will give something linear in beta. And it multiplies theta. So the action is something like half beta dot squared plus theta times beta dot. Then we consider the symmetry delta beta equals a constant. You apply Noether's formula to it. Okay, this is the symmetry which corresponds to electric charge. The whole way we introduce beta is that it is shifted by electric charge rotations. So the symmetry that generates shifts in beta is the electric charge, at least in this space of low energy excitations of the monopole. And QE, following Noether's formula, is the variation of the action with respect to beta dot. So it is beta dot plus theta. So the theta term shifts the values of the electric charge. I'm cheating slightly, and I can't quite see how to fix it at the moment. There's something I'm not quite remembering, but when we do this, we find, because of this term, that the values of the electric charge get shifted by a constant proportional to beta. So instead of the electric charge being an integer, which I'll call NE, it's actually an integer plus theta over 2 pi, except that we took the magnetic charge to be 1. The formula is really that the electric charge is an integer plus theta over 2 pi times the magnetic charge. It's better to write it that way in terms of integers, NE and NM. So an important example of the use of this formula, okay. Actually, there's something I forgot to tell you. So, okay. Yesterday we found that there were W bosons in small representations of supersymmetry. So that told us that the electric charge appears in the central charge. And we also deduced it at the end of the lecture when somebody asked the right question. And I did that little computation. But today we've learned that there also are magnetic monopoles in small representations of supersymmetry. And the only way for that to happen is that the magnetic charge is also in the supersymmetry algebra. Now, the mass of the monopole, when we calculate, turns out to be 4 pi over E squared times the absolute value of A. That's for magnetic charge 1. So we do this computation by solving the Bogomolny equations and calculating the mass of the classical solution. After we've done that, we get the correctly normalized formula for the central charge. And I did explain yesterday why there has to be a factor of I. As long as theta is 0, the electric and magnetic contributions have to be out of phase from each other by Cp. But I want to now generalize it to where theta is not 0. So I'm going to write it in terms of integers Ne and Nm rather than charges Qe and Qm, which are not always integers. So we write it as A times Ne plus theta over 2 pi times Nm plus I times 4 pi over E squared A times Nm. Or in other words, we write it as Ne times A plus nm times theta over 2 pi plus 4 pi I over e squared. That combination, which has just appeared, is very important, and it's often called tau. So that's the classical formula for the central charge, including the theta angle. Another derivation you could find, I gave you the reference yesterday to my paper with David Olive, where we just computed we did essentially the calculation I was showing you at the end yesterday in the question period, but a little bit more generally to include the magnetic charge. So you can do that explicit calculation to find the second term. So we got the classical answer, but it can't be right quantum mechanically because it doesn't make any sense. Tau is subject to renormalization. So one of our problems is to find the quantum version of this formula. Well, since we're mentioning quantum corrections, this is maybe a good time to remark that, first of all, the theory is asymptotically free. And that means it's going to be simple for large U. I told you this yesterday. Simple for large U, and our problem is to understand what happens for small u. Now, asymptotically free means in particular that the beta function is non-zero. And in supersymmetry, a beta function being non-zero is also related to a chiral anomaly. So we had this nice U1R symmetry where phi has charge 2, lambda has charge 1, and lambda tilde had charge -1. That's in the four-dimensional notation where I distinguish the four-dimensional chirality. It's a classical symmetry, but it actually has a quantum anomaly. It has a quantum anomaly in an instanton field. And one understands the quantum anomaly by counting the fermion zero modes in an instanton field. So in an instanton as opposed to an anti-instanton, lambda tilde has no zero modes. But the number of zero modes of lambda comes out to be 8. 4 because it's in the adjoint representation, times 2 because we're doing n equals 2 supersymmetry and there are 2 of them. So there are 8 lambda zero modes. So because there are 8 zero modes, the anomaly breaks U1 down to Z8. And you see, what we called U, which was trace phi squared, has charge 4. So Z8 acts by U to minus U. So let's draw the U plane again. Because there is an anomaly, the theta angle of the gauge theory can be rotated away by making a U1R transformation. But that transformation acts on u because u carries charge. So you can eliminate the microscopic theta angle in favor of rotating the field u by a phase. And we can define it so that the effective theta angle is 0 on the positive u axis. If we do that, then the effective theta angle is 4 pi times the argument of u. That's 2 times 2 pi. Sorry. The argument of u is the phase, but it goes from 0 to 2 pi. So the theta angle is 2 times the argument of u. What that means is that when u jumps, see, u going to minus u is a symmetry. Rotating u by a random angle isn't a symmetry because it changes the effective value of the theta angle. Rotating u to minus u is a symmetry. And what that means is that the theta angle has gone all the way from 0 up to 2 pi. So in general, the effective theta angle is twice the argument of u. So theta effective is 0 here. It's 0 also on the negative u axis. And it's pi, or equivalently minus pi, on these other axes. Now you could consider the electric charge of a magnetic monopole. Our formula tells us that if we increase theta by 2 pi, the electric charge QE increased by 1. So the electric charges are all possible integers. But if we pick one of those integers and go halfway around the u-plane at infinity, it'll get shifted by 1. And by the time we come back, it will have gotten shifted by 2. So if you want, there are two kinds of monopoles on the positive u-axis. The ones of positive even electric charge and the ones of odd electric charge. And under monodromy around infinity, those two groups don't get exchanged with each other. It might sound like a funny detail, but it's actually important. Any questions? So okay. Now, as a prelude to telling you how the theory works out quantum mechanically, there's another way of describing it that's really useful. So this is the third construction I promised, which overlaps with what John Bagger has been explaining. But I want to just review it briefly to get to orient ourselves to what we're doing. So here we work in superspace with coordinates x mu, where mu runs from 0 to 3. And then we will have two supersymmetries. So theta and theta tilde are my notations for the two types of coordinates of superspace. So they carry spinor indices of the opposite kinds, alpha or alpha dot. And in addition, since we're doing n equals 2 supersymmetry, they carry an additional index that the SU2R symmetry acts on. So I and j. And then in this space, supersymmetry is realized with a similar formula for Q tilde. the key to being able to write supersymmetric theories is that there are operators that commute with supersymmetry. The operators that commute with supersymmetry are magically found by just changing a sign. And similarly, for so the minus sign ensures that if you commute Q with D, you actually get 0. This hitting this cancels this hitting this. And, well, it should have been Q hitting D tilde, but the idea was the same. So supersymmetric theories are constructed by using the D's. And of course, the other important D is just D by dx mu, the spatial translation. Then you'd like to do gauge theory in superspace. So naively speaking, what gauge theory in superspace means is just that you add gauge fields in superspace. So you replace all the superspace, you replace all the covariant derivatives. Well, you replace D, you give D an internal gauge field, or a gauge field which has the same indices that D has. We call curly D the gauge covariant version of these things. And all these fields I've added depend on x, theta, and theta tilde. Well, what do we have if we do exactly what I've just said? We have a large collection of fields on which acts both supersymmetry and gauge transformations. It's obviously supersymmetric because we've allowed arbitrary dependence on x, theta, and theta tilde. And you see, if we act with Q, well, it commutes with D, and it will do something to A, but whatever it does is OK because we haven't said anything about what A is supposed to be. It has an arbitrary dependence on the fields. So this is a representation of supersymmetry, but it's not quite what we want. The reason it's not quite what we want is that it's got way too many fields. You can see this if we calculate d alpha I anti-commuted with d alpha dot j minus delta ij times sigma mu alpha alpha dot curly d mu. We could call this p alpha alpha dot ij. That's 0 if the gauge fields are 0. And because it is 0 if the gauge fields are 0, it's gauge covariant. It's analogous to a Yang-Mills curvature in superspace. You might not be used to having to subtract a first-order term, but the reason you have to subtract a first-order term is that if the gauge fields were 0, we're working in a sort of anholonomic basis. If the gauge fields are 0, the d's and d tildes don't commute. So we need to subtract the linear term to compensate for that in defining the curvature. And this is a dimension 1 Lorentz vector, which is gauge covariant. And it even has R symmetry indices, which is even worse. And there's nothing like it in n equals 2 super Yang-Mills. So we're going to set it to 0. But that's OK because it's a supersymmetric condition. Supersymmetry commuted with these guys. So this is a supersymmetric condition. we're going to now apply the same concept to commuting some of the fermionic guys with each other. For example, we take, so here we commuted a d with a d tilde. But suppose we commute two d tildes with each other. Okay, it's somewhere in my notes, but I don't want to take the time to look for it. Well, sorry. Okay. In general, we get something which, again, is gauge covariant. And that something has a piece which is anti-symmetric in its indices, and so is Lorentz invariant, or Lorentz spin 0, and it has a piece which is symmetric in its indices and is a self-dual anti-symmetric tensor. Well, it has dimension 1, and we don't want a self-dual anti-symmetric tensor of dimension 1. I'm getting dimensions because the d's have dimension half, this kind of d, and an ordinary derivative has dimension 1. So we don't want the symmetric part, so we keep only the anti-symmetric part. So we get a scalar field in superspace, which is of dimension 1, and it's a scalar in the adjoint representation. That's okay because our theory has such a field, which earlier on we called it A4 plus IA5, which we also called phi. So this capital phi is going to be that phi plus stuff of order theta. It has an expansion in powers of theta that has in it exactly the things we want. So we've imposed a bunch of conditions, and they're all supersymmetric conditions because of the fact that they're defined using the d's which commute with the q's. And there's one more beautiful fact, which is that this is 0. And this happens to be a computation that is best done not covariantly. I'm going to show that a particular component is 0. Let's say d1.1 of phi. And then from our formula up there, phi can be written in several ways. But one way we can write it is that phi is the anti-commutator of d1.2 with d2.1. Sorry. I've chosen a representation of phi where either the Lorentz index or the internal index matches that on the d that we're studying. So when we use the Jacobi identity to simplify this guy anti-commutes with both this guy and this guy. So we got 0. So phi is a chiral object. It only depends on half of the components of superspace. And hence we can write a Lagrangian. We pick a holomorphic function, curly f of phi, and we write an action which is the imaginary part of the integral d4x d theta alpha I of f of phi. Okay. I'm shortening a couple steps slightly. What you do is you conjugate the condition that f is annihilated by the d's. After conjugating a little bit, it says that it's independent of the theta bars. Since it's independent of the theta bars, or theta tildes I've been calling them, we can integrate it over the thetas to get something. But that something would be complex. It wouldn't be real. So we take the real part, except it's traditional to call it the imaginary part. Since I didn't tell you what f is, it hardly matters. F is a holomorphic function. If we change f by a factor of I, we would call this the real part. So this is a general way to construct n equals 2 supersymmetric theories, which I think you've also heard something about from John. And the reason I've presented it is that it will help orient us to what we have to do to actually solve our theory quantum mechanically. But before I do that, just having gotten this far, I'll tell you something about the ultraviolet. So the microscopic definition of the SU2 theory we take f of phi to be tau times the trace of phi squared. I took the trace because phi is in the adjoint representation. So I take the trace to make it SU2 invariant, gauge invariant. Then I multiply by an arbitrary complex parameter, tau, which has been introduced before. And after we do the d4x, d4 theta integral, we get the same Lagrangian that I've been telling you about. This is our third construction of it, except I don't have time to spell out all the details. What we actually need for today's lecture, or the rest of today's lecture, is not the microscopic theory, but the infrared theory. So the infrared theory had SU2. Okay. We had this U plane, and classically there was a bad point at the origin, but quantum mechanically there's a bad region near the origin where the gauge coupling becomes strong and we don't trust the classical behavior. But at least, so we don't know what's going on in here. Unless you, okay. But for large U, there's a classical picture. SU2 is broken to U1, and there's a single phi field. Phi has an expansion that I'll call A plus theta lambda plus theta squared times the self-dual part of F mu nu. And then the last term is theta to the fourth times the Laplacian of A bar. You might be curious, incidentally, how the last term turns out to be A bar. That's a good exercise, too. The last term is what you'd get if you acted on phi with 4 d's. And phi itself is the commutator of 2 d bars, or d tildes. So to compute this last term, you have to use the Jacobi identity a lot of times. And you would use the fact that d with d tilde is an ordinary derivative. So each d tilde will go away in favor of a derivative. And you have 2 extra d's, which will turn into an A bar. So after some work, you'll find out that phi has an expansion where the last term is the Laplacian of A bar. I didn't tell you that as a random fact. We actually need it, unfortunately. So, since the low energy gauge group is U1, and the adjoint representation is trivial, any holomorphic function f of phi makes sense. And the low energy theory is given by some effective action, the imaginary part of d4x, d4 theta, of some f of phi. And if we could find f of phi, then we would feel we understood the theory. Now, I'm kind of out of time, but I'm going to take advantage of the fact that there's nothing scheduled. So if our stamina holds up, we can keep going. But as you can see, what I've done is to not, in these two lectures, really explain Seiberg-Witten theory. Rather, what I've explained is the things that you should know before trying to read our paper. You're now ready to read the paper. It's true that I didn't fully think it through when I announced the title and also when I assigned our paper as the reading you should do. I should instead have looked at the references of our paper and figured out what were the best ones to suggest as the preliminary reading. Certainly my paper with Olive would have been one. Another would have been the work of Grimm, Sonius, and Wes, I think it was, on this superspace formulation. And I think the electric charge of a magnetic monopole would have been a good thing to study. And one of Seiberg's papers from the 80s I should have put on the list. Anyway, the reading should have been preliminary reading. But now we're ready, if you want, to read the paper. And we're also ready to explain it. It's just that we're also at the end of our lectures. But it's a pity to stop now, so we won't. So, first of all, classically, for the SU2 theory, tau f was trace of phi squared. And then if we just let phi be a and minus a, I guess to literally make this work out, I should divide by the square root of 2. Then we would find that f for the U1 theory at the classical level is a squared times tau. But we'll maybe call it tau classical. However, there's something called asymptotic freedom. So we can't simply have tau classical. It's not renormalization group invariant. There's a one-loop correction. And the one-loop correction is I over 2 pi times a squared times the logarithm of a squared over lambda naught squared. I'll show you in a second that one-loop correction incorporates asymptotic freedom. Now, I've written lambda naught rather than lambda for the renormalization scale and the one-loop correction. The reason I have is that once you've got this logarithm, this one-loop correction, by shifting the scale of the logarithm, you can get rid of the classical part. So we might as well just write this as I over 2 pi times a squared times the logarithm of a squared with a different lambda. So not only is there a one-loop correction, but the classical piece we don't really care about. Now, whatever f is, we'll discuss the implications in a second, but let's first work out the action for any f. Given this expansion, you see that, okay. Let's just find some interesting terms. So one interesting term is the kinetic energy of A, which comes by doing the theta integral all at once with the theta to the fourth times box A bar. So we take dF, it's the imaginary part of all this. We take dF dA times box A bar. On the other hand, the Yang-Mills curvature multiplies 2 thetas. So to get up to 4 thetas, we'll have to expand twice and take the quadratic part of the curvature. So that'll give us a second derivative of f. Where plus means the self-dual part of f. And there are fermion terms, but we won't need the details. So our action looks something like that. Well, okay. So in general, you see what multiplies f plus squared in general is tau, the coupling parameter. In general, tau effective of A, which I'll just call tau, is d2f dA squared. Now, that's a troublesome formula because tau is supposed to be theta over 2 pi plus 4 pi I over e squared. And therefore, the imaginary part of tau is supposed to be positive. But it's impossible for the imaginary part of a holomorphic function to be positive everywhere. Basically, it's impossible. I should tell you a couple of more facts, but the minimum modulus principle for holomorphic functions won't allow it. So we'll have to do something to get a sensible theory. But first, let's discuss a few things that do work. So we should at least look for asymptotic freedom. So in the one-loop approximation, we see that tau effective is d2f dA squared. And so taking the second derivative of that, we get I over pi times the logarithm of a squared over lambda squared. So I could differentiate the logarithm, but I'm not bothering because it would give a subleading term. So if you want, the constant term just changes lambda again. So the effective tau looks like that. And remembering that that's equal to the effective theta over 2 pi plus 4 pi I over the effective e squared, you see that 4 pi over e effective squared goes like 1 over pi times the logarithm of absolute value of a squared over lambda squared. So 1 over e squared grows logarithmically at infinity. That's called asymptotic freedom. Another fact which we see is that theta effective over 2 pi is, looks like it's minus 1 over pi times minus 2 over pi times the imaginary part of log A. Now, on the u plane, u is a squared. So if u undergoes a monodromy at infinity, a undergoes a half monodromy, and log a rather, picks up I pi. So theta effective over 2 pi is shifted by what would be, if we got it right, plus 2. Yeah, we did get it right. So a is shifted by pi, log a is shifted by pi, which cancels the pi. So we just get a 2. So I told you about that before. This reflects the U1 anomaly, that the effective theta angle changes near infinity when we go around a big circle in the U-plane. Because changing U could have been removed by a U1 rotation, but that has an anomaly which will shift the value of theta. So what we've discussed so far are the interpretation in this language of the one-loop term. Now, there actually are no higher order perturbative corrections. And the reason there are not is perhaps most succinctly stated by saying that f of A and the bare coupling, tau classical, is actually holomorphic in tau classical. That can be proved using supersymmetry. You'll find the argument in our paper, but I think it's one detail I'd better resist the temptation to explain. So, you see, the trouble with being holomorphic in tau classical is that tau classical depends on theta. So, if you're not allowed to have theta dependence, you can't have tau classical dependence. Now, an L-loop contribution is proportional to tau classical to the 1 minus L. See, in general, in quantum field theory, an L-loop contribution goes like the coupling squared to the L minus 1, which in our language would be tau classical to the 1 minus L. Now, L equals 0 was okay because the classical action contained theta. So if L is 0, that just says that the classical thing is linear in tau, which it was. L equals 1 is okay because 1 minus L is 0. But L bigger than 1 is not okay because to be holomorphic and behave like this, it would have to actually depend on theta, which perturbation theory doesn't. So there are no perturbative corrections to this formula. It's exact to all orders of perturbation theory. You could ask, therefore, is it exact? And the answer is that it can't be exact because it doesn't make sense. If you look at our formula for 4 pi over e squared, it's not positive definite. It's proportional to the logarithm of the absolute value of a, so when a becomes too small, it would become negative. So although there are no perturbative corrections, there have to be non-perturbative corrections. Those are corrections due to instantons. There's no contradiction because instanton contributions do depend on theta, so therefore they can be holomorphic on tau, in tau. In fact, in Seiberg's lectures, you'll hear a lot about, mostly for n equals 1, supersymmetric instanton corrections that depend holomorphically on tau. Now, even with non-perturbative corrections, if the answer were to be written in this language, we'd be in trouble because, as I've told you, the imaginary part of tau being the imaginary part of the holomorphic function wouldn't really let it be positive definite, even if we add non-perturbative corrections. So what's going to save the day is a new ambiguity in the effective action. A new ambiguity in how the low energy description is made. So we already used the fact that the low energy description is not unique. We have the possibility of tau going to tau plus 1. In other words, theta going to theta plus 2 pi. But there's another non-uniqueness in the low-energy description of an abelian gauge theory in 4 dimensions. It's similar to things that Katrin Becker has been describing, at least in the homework session yesterday. The further ambiguity is electric-magnetic duality. So classically, electric-magnetic duality exchanges the electric and magnetic fields. But quantum mechanically, by a manipulation similar to the one that was presented in the homework session, it acts by tau going to minus 1 over tau. And we're going to have to exploit this ambiguity of the low-energy theory. So I actually have to tell you a little bit more of a word about the classical action. There's something that I think got erased. But the part of the action that gave the kinetic energy for the scalars, when we last saw it, it looked like this. But we're going to integrate by parts. And so the metric, the metric on A space is the imaginary part of d2f dA squared times dA tensor dA bar. And once again, we see we're in trouble if the imaginary part of d2f dA squared isn't 0. Isn't positive. But there's something fun which we can do. We introduce a new function, a dual of A, which is df dA. It's funny how useful that is. So the first fact is that tau, which was d2f dA squared, we can write as dA dual dA. But we can also write the kinetic energy in an interesting way. This thing here, you see, using the chain rule, you can write it as the imaginary part of d mu a dual times d mu a bar. Or if you want, you can write it as integral d4x d mu a dual d mu a bar all I've done is to use the chain rule. I've just used the fact that in view of the definition of d mu a dual, d mu of a dual is d2f dA squared times d mu a. So we got rid of f at the cost of having this unknown function a dual in there. Now, the purpose of introducing a dual is the following. If you look at the transformation of electric-magnetic duality, tau goes to minus 1 over tau. You'll see that it acts on a dual in A by a dual in A going to plus or minus a and minus a dual. There's no natural choice of the overall plus or minus sign. That actually corresponds to charge conjugation of U1 gauge theory. It is important that there's a minus sign We exchange A and A dual, but with a minus sign. That has the effect that dA dual dA goes to minus dA dA dual, which is minus 1 over dA dual dA. In other words, tau goes to minus 1 over tau. What that means is that there are two low energy descriptions. One is by fields A dual, and tau, and the other is by A dual minus A and minus 1 over tau. And this description also has a photon. This other description has a different photon. There's no simple formula that explains how the two photons are related. They're related by exchanging electric and magnetic fields. And there is a simple formula for the fermions, but I won't explain it. So I haven't given a more complete explanation is given in our paper for why this is a symmetry of the, why this corresponds to two equivalent descriptions of the same low energy theory. We can also improve upon the formula for the central charge. The last version of it that we saw was this one in terms of the classical A. But remember that if F is 1/2 A squared, then A dual times tau, which is dF dA, is just tau classical times A. So a better formula for the central charge is this one. It has the virtue of being a renormalization group invariant, because A and A dual are meaningful fields in the low energy theory. And also being duality invariant. In our paper, you'll find a more complete explanation of why it's the right formula, but we'll have to skip that here. So let's give a unified explanation of the ambiguity in the low energy description. Theta going to theta plus 2 pi means tau going to tau plus 1. Tau is dA dual dA. So tau going to tau plus 1 means that A dual is shifted to A dual plus A. I think I'd rather write it in terms of column vectors. So A dual and A goes to this matrix times A dual and A. Electric magnetic duality which was tau going to minus 1 over tau, maps A dual and A like so. These matrices are the usual generators of SL2Z, usually called S and T. S and T generate the group SL2Z. So the low energy effective description of this theory by a single vector multiplet of n equals 2 supersymmetry is only unique up to an SL2Z transformation. Okay. So an example of this formula is this following. Let's just check that it makes sense. The central charge has to be independent of the description we use because it enters into mass formulas, or for that matter, the commutation relations of the supersymmetries. If A dual and A transform to some SL2Z matrix times A dual and A, then we have to transform NM and NE to themselves times M inverse. But if M is an SL2Z, in other words, it's an integer-valued matrix of determinant 1, M inverse also has integer values. So this is an integer-valued transformation of electric and magnetic charges. So our formula for the central charge is independent of the choice of a low-energy description, in addition to its other advantages. Now, let's discuss why, or what the answer might be for this theory. The classical answer on the U-plane was that there was one bad point. Then, away from that point, the U1 description is good. And the monodromies were the SL2Z monodromies, but the fundamental group of the U-plane with 1 point removed is abelian. The only monodromy would be the monodromy at infinity. And that monodromy is a shift in the theta angle that left A as a good coordinate. You see? What is the monodromy at infinity? In other words, under, so to speak, U going to e to the 2 pi I times U. Well, classically, since A is the square root of U, A would change sign. And since A dual is tau times A classically, it would also change sign. So that would be the classical answer. But there was a shift in the theta angle at infinity. So actually, A dual picks up 2 times A in addition. So the monodromy at infinity is A dual and A and it has the property that A squared is invariant. Now, if there was only one bad point, which is the answer quantum mechanically, the answer classically, then the monodromy at infinity would be the only monodromy, and A squared would be a good coordinate. That would be very bad, because then we'd be back in the situation where the imaginary part of tau can't possibly be positive definite. So there has to be more than one singularity so that there can be non-abelian monodromies that will really use electromagnetic dualities. Well, if there's more than one bad point, there are at least 2 of them. And since there's a symmetry U going to minus U, if there are 2, then neither one of them is at U equals 0. So the minimal picture has 2 singularities, which are at non-zero values of U, which we can call lambda squared and minus lambda squared, where lambda is a mass parameter used in renormalizing the theory. So from the classical point of view, lambda is exponentially small. It's lambda, if you want, is the mass scale at which the theory became strongly coupled. So classically, there was one bad point at U equals 0, but quantum mechanically, there are 2 bad points that are exponentially small and not at 0. So Seiberg and I were able to show that if you assume that there only are 2 bad points, then you find a unique solution that has all the right properties. And moreover, there was an a priori reason that there only are 2 bad points. The a priori reason has to do with confinement. I want to let you go at a reasonable time. So we have to cut a few corners. Maybe I'll stop for questions while I'm trying to decide which corners to cut. No questions? Yes?
How you normalize U equals to lambda?
Well, I haven't told you what the renormalization scheme is. So in my paper with Seiberg, we just used an arbitrary renormalization scheme. We actually called it 1 by choice of units. So what makes your question interesting is if you have a renormalization scheme that's motivated in some other way, for example, MS bar regularization. If you're using MS bar renormalization, then the bad point is at a definite constant times lambda squared. And you can compute that constant of some given renormalization scheme. Any other questions? Presumably you're not asking questions because you want me to finish as soon as possible. Okay. That probably means I should cut a few extra corners. So the proposal in our paper is that, well, what would, in general in physics, what would be a bad point where something goes wrong in a low energy effective description? There can be something called a first order phase transition where something goes wrong without warning. You're watching a tub of water, somebody's cooling it, and suddenly it freezes. Nothing was wrong with the water except suddenly it became thermodynamically unstable to something far away. You didn't see any light degree of freedom in the tub of water before it suddenly froze. Here, though, if we're looking at an isolated singularity, it's much more reasonable to assume that what's happening is that extra massless particles appear. So our proposal was that the nature of the singularity is that there are extra massless particles and if there are extra massless particles, then, well, you have to include them in the low energy effective description, otherwise you have a bad description. So that would be why the description is bad at those points, and there would eventually be monodromies around them. So in the classical story, there are extra massless particles at u equals 0, but they are vector multiplets. It turns out that it works much nicer if you assume that quantum mechanically the extra massless particles are hypermultiplets. So the hypothesis is that the theory has massive hypermultiplets, some of which become massless at the two bad points. But if that's going to happen, the massless hypermultiplets should not have only electric charges for two reasons. One reason is that it wouldn't help. As you'll see shortly, an electric hypermultiplet getting massless would not solve our basic problem. But a more basic problem is that the theory doesn't have electric hypermultiplets that only have electric charge. The only hypermultiplets we found are the ones that have magnetic charge. They may have electric charge as well, but by quantizing the Bogomolny equations, we got magnetically charged hypermultiplets. So the hypothesis is that some of those magnetic monopoles that were very heavy when last seen at strong coupling actually become massless at the two bad points. Now, let's discuss what happens if a monopole mass, let's say with nm equals 1 and ne equals 0, goes to 0 mass. Well, the first thing is that if there's a light monopole, we better not use the description by the usual gauge field that coupled to W bosons. It's very hard in that description to see a light magnetic monopole. We should use the electric magnetic dual description. So we use A dual and the dual photon, not A and the original photon. After doing that, we can treat the monopole just as if it were electrically charged. And now we face the fact that QED is not asymptotically free. So in the infrared, the gauge coupling of U1 with massless charged particles goes to 0. So there's a one-loop correction, and tau dual, which is, let tau dual be minus 1 over tau. Tau dual goes like the logarithm of A dual, well, where A dual goes to 0. Maybe I shouldn't call the point 0. Well, okay. We'll call it A dual equals 0, the bad point. So there's a precise constant in that formula that comes from the one-loop beta function. Tau dual is actually minus I over pi times the logarithm of A dual. That's from the fact that QED is not asymptotically free. It's the one-loop beta function of QED. QED, the same argument as in the ultraviolet, there are no higher perturbative corrections. But also QED doesn't have instanton, so there are no instanton corrections. But more than that, this formula makes sense all the way down to A dual equals 0, so it doesn't need any corrections. So tau dual is dA dual. So you see that if dA dual is a logarithm, well, first of all, around A dual equals 0, tau dual has a monodromy. Tau dual goes to tau dual minus 2. So that means that A goes to A minus 2 A dual. Nothing happens to A dual because A dual is a good coordinate in this description. So A dual and A are going to themselves times some other matrix. So now we have a monodromy at infinity. Let's draw a less cluttered version of the picture. Here's a loop at infinity. And this is a loop around lambda squared. And here's a loop around minus lambda squared. So m infinity was this, and m lambda squared was this. So since m infinity is m minus lambda squared times m lambda squared, we can find what is m minus lambda squared. And an important fact is that we get a sensible answer. First of all, the trace is 2, so that m minus lambda squared is conjugate to m lambda squared. Remember, there's a symmetry u going to minus u, so they have to be conjugate matrices. And more fundamentally, this is the monodromy due to a massless dione with nm and ne equal to 1 and 1. So a monopole becomes massless here, and a dione becomes massless here. I think I'm going to try to drastically shorten this so I can finish up. So I'll just make a couple more remarks. What we found now is a flat SL2Z bundle over the U-plane with 2 points removed. But this has a nice interpretation. So first of all, tau modulo the operation, tau going to u tau plus v over x tau plus y, where u, v, x, and y are integers, and the determinant of the matrix is 1. See, that's the gauge invariant combination of tau, because our basic ambiguities in the low energy description, we worked it out for 2 particular matrices, but they generate the full group of all such matrices. These were our examples. But by iterating these transformations, you could get a general integer-valued transformation of tau of that form. The invariant information contained in such a tau is the information in a Riemann surface of genus 1, what people call an elliptic curve, which you can think of as gotten from a lattice in the complex plane, where the basic lattice vectors, apart from the origin, are 1 and tau. If you replace tau by u tau plus v over x tau plus y, the coefficients all being integers, that corresponds to taking a different basis of the same lattice in the complex plane. So the situation I've described is that over the twice punctured U-plane, we have a family of genus 1 Riemann surfaces, a family of elliptic curves that depends on U. If you look in the right book, you find a convenient explanation of a family of genus 1 curves that depends on a parameter U and has exactly these monodromies. I guess we were lucky to find the right elementary book that had it. It can be described by this explicit equation. And it turns out that the whole solution of the model can be written in terms of that family of elliptic curves. So I've mainly, it's pointless to even try to list the things I'm not telling you, but they're in 2 basic classes. One class of things, given this family of elliptic curves, first I should take more time and tell you why they have the right monodromies and all that. But given that family of elliptic curves, how do you write formulas for everything? That means A dual, and tau in terms of that elliptic curve. And the other type of question you might ask is, how would you determine that this solution is correct? In other words, what properties does it have that agree with what properties the model should have? So there are a lot of things I've told you, like how A and A dual behave near the singularities, which you can extract from this family of elliptic curves. But there's something very important I haven't told you about, which is the link to quark confinement. If you perturb the model slightly by reducing from n equals 2 to n equals 1 supersymmetry, by giving a mass to the chiral superfield, it becomes a model. So we take a superpotential, by adding a superpotential the model is expected, just like QCD, to become confining in the infrared and to have a vacuum which is unique except for a 2-valuedness that comes from a broken chiral symmetry. Now, it's also known that heuristically, confinement could come from condensation in the vacuum of magnetic monopoles. And if a magnetic monopole becomes massless, it might become tachyonic and condense under a further perturbation. So the most interesting idea in our paper that I haven't had time to tell you about is that we showed that the monopole and dion that become massless at those points, under a further perturbation, exactly the perturbation where confinement is expected, they actually become tachyonic and condense, leading to quark confinement. So the most interesting thing that came out of the paper physically, well, okay, we could solve it, the model, and there were all kinds of funny things, solitons becoming massless and so on. And the solution involved ingredients that weren't used before in solving, well, the role of electric-magnetic duality was certainly interesting and had other applications. But in terms of understanding gauge theory better, perhaps the nicest thing was just that the idea of confinement due to condensation of monopoles became more precise. I think I've done what I reasonably can. We've kind of explained most of what you should know in order to read the paper, and I've given you a synopsis of some of its contents. Thank you.